Last three videos, we talked about the electron. Now, originally, the electron wasn't thought to be, well, it wasn't considered to be an electron. There were these electric waves that went through the air, and there was no reason to believe at that time that they weren't just continuous waves. So J.J. Thomson found out that we had this charge to mass ratio, and it started acting like a mass which was 1,000 times less than hydrogen. Now, here's another thing that's involved here. When you have gas molecules or other mass molecules that are ionized, they are deflected through space. So the thought was that these electron charges were in the atoms, and so those electrons were part of that. My main point today is that the idea was that there was a quantity of charge. You can't have less than the smallest charge that an electron holds. Can't get any smaller than that. That is the elemental charge. And so that's a very important piece of the universe. Now, electromagnetic waves, the light that's shining on my face right now, those electromagnetic waves can be produced by what? Let's see. You could have fire could produce light, but what's the most common thing that we're used to is electric lights. So what's causing that light? The movement of electrons are causing the light. So what about the light that's created from that? Somebody did some research, and the name was Planck, and he said, I'm going to find the relationship between temperature and radiation by heating that wire that glows. There must be a relationship between the temperature of that wire. In other words, that's how fast everything is moving inside that wire. The kinetic energy, the average kinetic energy, which is temperature, and the electromagnetic wave that is coming across it. So the thought was that he would have a relationship that would match every temperature to a wavelength of light. But guess what happened? It turned out that it seemed to skip. There were little levels where that light frequencies wouldn't occur. And it happened to be different by this one constant. And because Max Planck couldn't figure it out, he used this quantity as an H. And he was saying, help, this isn't right. This isn't what I expected at all. I expected there to be a continuous spectrum of light from every temperature that I could give. There would be an equal and similar light that would come across that. But it didn't work that way. And what happens is, just like with the electron, they thought that was a continuous, or not a continuous, yes, a continuous piece in the cathode ray, that you could have any amount of charge down to zero that went and turned out that there was an elemental charge that was on this. We called this charged particle an electron, and that electron happens to have mass. So why wouldn't the same thing happen with light? With light, you can have these quanta, and because they came up with this term electron, and because the word photo was used. Let's see, what would the relationship of photo be? What would that be before we started talking about photons? We had photographs, so that was evolving light. And so we have this name photon. So the relationship between let's call it a quantized piece of electricity, this elemental charge, we have a quantized piece of light that is caused by the electrons moving around, and then we have these photons that occur. So that kind of makes sense. At least it does to me. And here's another thing that's really curious that we want to examine. The electron was a charged particle. It had a certain charge. So if you put charged plates on either side of that, it deflects the beam. If you put a magnetic field on that, it deflects the beam. But if you shine light through those charged plates, or you shine light through a magnetic field, it doesn't get deflected. So we could use an idea that if it has mass and it's charged, then it will get deflected. So we could say, well, is it charged? Well, it's electromagnetic, but it doesn't have any mass. So the charge reflection would say that the photon has no mass. This will require some math to get some numbers out of this thing. In other words, how big is a photon? What frequency is a photon? Does the electron have a frequency? They should be related. If a photon you think of as a frequency packet, then why couldn't the electron, when it's moving, be a frequency packet? Let's try to bring those two ideas together with a slide that has some numbers to go along with it.